So I've started a separate part for our proof of Euclidean division. So I've copied just a few of the notes from the previous part, which are going to be helpful to us. So in this proof, we're going to split it up into a huge number of different cases and prove that the theorem is true in these separate cases. And then, because once we've done enough cases that cover every single possibility, we'll then have proven it for every possibility. So let's do this. So we'll start off with a quite trivial case, which is the case when a is equal to 0, and we'll let b vary over all the values it could be. So over all integers, except of course it's not ever allowed to equal 0. So the theorem is going to be trivially true in this case. So I need to show you that I can find a q and an r such that r obeys that inequality. So here is my q and my r. I can make q equal to 0, and I can make r equal to 0. So a is 0, so I can put q as 0, 0 times b is 0, and then I'll just add on remainder 0 as well. So q and r are both 0. This equation is true, and r here is going to satisfy the inequality because b is non-zero, so its modulus therefore is going to be greater than 0, 1 or more, and therefore r putting in 0 here does obey this inequality. It's equal to 0 and it's less than the value of mod of b. So absolutely fine. Theorem is true if a is equal to 0. Then we're going to next do the case that a is greater than 0 and b is greater than 0. So both of them we're going to assume are positive values. After we've done this case, we'll look at the case where a is greater than 0 and b is less than 0. And then we'll move on to the case where a is less than 0 and b is greater than 0, and a is less than 0 and b is less than 0 finally. Once we've done all of that, we'll have proven it for every single possibility. So to prove this case, we're actually going to split it into two cases again. We're going to split it into the case that 1, b is greater than a, and the second case will be that b is greater than 0 but less than or equal to a. So let's start off with this case because this is more trivial. So if b is bigger than a, then it's really obvious what you can do. You can just make the quotient 0, so have 0 times b, and then make the remainder a, because remember both of them are positive numbers now. So if we do this, mod of b is just going to equal b. So a we're saying now is smaller than b. It's a smaller positive number. So you can make the remainder equal to a and it will still satisfy this equation. On the number line, if we have our integer number line here, you might have imagined that a is here and now b is actually bigger than it. So it's a silly thing to do really. It's a silly case. We're dividing through by something that's bigger than the thing we're actually dividing. The divisor is bigger than the dividend. So in this case, we're just going to make, say, 0 amounts of the divisor go into the dividend, and the remainder is equal to the size of the dividend, which does then satisfy this inequality. So that one is a trivial case as well. Now let's do this case, which is the proper case. So we want to show that if a is greater than 0, a positive integer, and b is also greater than 0 but less than or equal to a, that this theorem holds true. And the way we're going to do this is a proper proof at long last. We're going to do this by induction on a. So we'll start off with the case that a is equal to 1, and then we'll do the inductive step, and then once we've got the inductive step, it will then follow that it's true for a is equal to 2, and then a is equal to 3, a is equal to 4, etc. So let's start with the case a is equal to 1. So in that case, we need to show that for all b's that you could pick that satisfy this inequality, so that in between 0 and a, that the theorem is going to be true. So in the case that a is equal to 1, there's only one b you could pick, because it has to be bigger than 0 and less than or equal to 1. So there's only one integer that does that. So b is also going to be equal to 1 in this case. And therefore, we just need to check that this obeys that division formula. So we need to find a q and an r. So just make q equal to 1, and then the remainder just needs to equal 0. So that satisfies the inequality because this remainder is smaller than b. It's equal to 0, which is allowed to be, and it's smaller than size 1. So that's excellent. So it's true for a is equal to 1. Now we're going to do the inductive step, and I'll write this out in full to make sure everyone understands it. So we're going to assume it's true for a is equal to k, i.e. if you pick any integer b, I'll put that b is an integer, between 0 and less than or equal to k, so pick any b that satisfies this inequality, so 1, 2, 3, 4, 5, all the way up to k, for all of them, this theorem is true, i.e. you can write a is equal to q times b plus r, where q and r are both integers, and r will satisfy this inequality of being greater than or equal to 0 and less than, strictly less than the modulus of b. Now, we want to show that if that's true, so we assumed this bit as part of for the purpose of induction, we assume that, and we want to show that for a is equal to k plus 1, the theorem is also going to be true. So we need to show that for all b greater than 0 but less than or equal to now k plus 1, that the Euclidean division works. So we'll start off with the case that b is equal to k plus 1, because that's the one where we can't use the previous assumption that we've made. And then for b is greater than 0 but less than or equal to k, we can then use the inductive assumption. So firstly, if b is equal to k plus 1, then clearly Euclidean division works, because we can just write k plus 1 is equal to 1 times k plus 1. So k plus 1 is equal to make q 1, and then you need 0 remainder. So clearly that's going to satisfy this inequality. So tick, it's done for b is equal to k plus 1. So we now just need to look at all the other b's. So b is greater than 0 but less than or equal to k, the integer under k plus 1. And for this one, we can apply the inductive assumption. So we know that for a is equal to k and b is greater than 0 but less than or equal to k, Euclidean division works. So we can write, therefore, k is equal to q times b plus r, where r is guaranteed to obey our inequality. And this is it as long as b is in that slightly smaller range, so greater than 0 but less than or equal to k. So we can write this for all of these b's. Now what we can do is we can just add on 1 to both sides, and then we'll have k plus 1 is equal to q times b plus r plus 1. So this looks very hopeful that from our inductive assumption we will be able to derive that Euclidean division is going to work for k plus 1 for all of these b's in this range, as long as r plus 1 is still satisfies this inequality. So we need it to be the case that r plus 1, well, clearly it's going to be greater than or equal to 0, because r was greater than or equal to 0, so r plus 1 is definitely going to be greater than or equal to 0. But the bit that we're slightly worried about is what if it's not less than b? So if it is the case that it's less than b, fantastic, you're done. If it's not less than or equal to b, well, that must have meant that r must have been the integer 1 below mod b. Remember, mod b is an integer, r is also an integer. R had to be less than b by our inductive assumption. So if r plus 1 is somehow not going to be less than b, it must have meant that r was the integer mod b minus 1. And then when you've added 1 here, it's gone up to mod b, and therefore it no longer satisfies this inequality because it's not strictly less than b, it's actually equal to b now. But in that case, of course, you have gone up or down a whole multiple of b. If b is a positive number, mod b is equal to b, and therefore you've gone up by a multiple of b, so you can factor this into the q as q plus 1 times b. If b is a negative number, then mod b is equal to minus b, so to put it in here, you'll have to have q minus 1, so you've gone down by a multiple of b if b is a negative number. But the point is that if r for k was equal to this, then for k plus 1, it's going to be equal to mod b, and therefore it's going to turn out that k plus 1 is a perfect multiple of b in that case. So it works overall. Let me just explain this again because this is really crucial. So the inductive step that we've made here is we've assumed that for a is equal to some integer k, that it is true that whatever b you pick within this range, so greater than 0, less than or equal to k, Euclidean division works. We are then trying to prove that for the bigger integer, a is equal to k plus 1, for its slightly bigger range now, from b is greater than 0 to less than or equal to k plus 1, that again Euclidean division works. And if we've done that, then we'll have the inductive step. We split this into two cases because for the case that b is k plus 1, we couldn't use our inductive assumption, so we had to consider that separately. But that's actually really trivial because clearly when b is equal to k plus 1, the Euclidean division holds true. Then for all the other b possibilities, so b is greater than 0 but less than or equal to k, we could use the inductive assumption. So we knew that we could write k is equal to q times b plus r, where r was going to satisfy this inequality. And then we've said, oh, we can use this to find a Euclidean division for k plus 1. Just add 1 onto both sides, and we get this. We then need to check that our new remainder, this r plus 1, is still going to satisfy this inequality. So the only case we have to worry about is what if previously it was just 1 below mod b? What if previously it was equal to mod b minus 1? Well, in that case, when you go up to k plus 1, it's going to end up being a perfect multiple of b, because r plus 1 is now mod b, which you can then swallow into the quotient here in the two ways that I've discussed. If b is positive, it just becomes q plus 1 times b. If b is negative, it becomes q minus 1 times b. So that's the only case you have to worry about. In all the other cases where r is smaller than this, an integer further away from mod b, then adding 1 will still be in this range, and you'll therefore still be able to do the Euclidean division. For that case, it doesn't matter because it's just going to become a perfect multiple that therefore still satisfies Euclidean division, because now, of course, the remainder is 0, and therefore it satisfies this inequality. So what I have proven is that if it is true that for a is equal to k, that for all integers b greater than 0 but less than or equal to k, Euclidean division holds, then it is also true that for the next integer along, for all integers that are greater than 0 but less than or equal to this bigger integer, k plus 1, Euclidean division holds true. So therefore, because it is true for a is equal to 1, that everything in this range for b, Euclidean division holds true, then I can conclude for 2 it holds true, and then for 3 it holds true because it's true for 2, and then for 4 it's going to hold true because it was true for 3, and therefore we can conclude that 4a is greater than 0 and 4b is within this range from 0 greater than 0 but less than or equal to a. The Euclidean division is going to hold true. Together with what we've shown already about b being greater than a, we can therefore conclude that for any a greater than 0 and b greater than 0, Euclidean division holds true. So let's now do the remaining cases, and the remaining cases are going to follow from this one that we've proven. So let me show you how this works. So this is quite cool. So let's firstly do the case where a is still positive, but now b is a negative number. So what we simply do is take the modulus of b, which is going to be a positive number, and then apply what we've shown for a and b both being positive, and then we'll use that to show that it's going to be true in the actual case that we want. So if we consider mod of b, because mod of b is going to be greater than 0, we can now use what we've shown, i.e. that the Euclidean division is true for 2 positive numbers. We can use it on a and mod b. So I know that I can write a as an integer quotient times mod b plus r, where r is going to satisfy this inequality. So it's going to be greater than or equal to 0, and it's going to be less than the modulus of mod b. But of course, mod of mod b is just mod b. Good. So now I want to use this to show that I can find you a way of writing this in terms of b that is also going to satisfy the Euclidean division property. So I know that mod b is just equal to negative b, so b was a negative number, therefore mod b is just equal to minus b, which is the positive version of it. So I can now replace this with negative b here, and all I need to do is actually make q negative. So if I do this, it's going to be a is equal to q times minus b, but of course minus b is just equal to minus 1 times b plus r. So then by associativity we can take that minus sign into the q. We can multiply q by minus 1, and therefore this is going to be equal to a is equal to minus q times b plus r. So if q was an integer, then negative q will be an integer. So I've now got, look, a is equal to an integer. This is my new quotient. Negative q is the quotient now, times b plus r. And I already know that r satisfies this inequality, so that's perfect. So we've proven, therefore, that Euclidean division works in this case. Next, and we're going to do all of the other two remaining cases in exactly the same way. Gets a little bit more complicated, but not too much. So next we'll do the case where a is negative and b is still positive. And then we'll do the case where a is negative and b is negative. So again, we do the same thing. We take mod of a, which is going to be greater than 0, and we now apply what we know already about Euclidean division for two positive numbers to mod a and b. So we say mod a can be written as q times b plus r, where we know now that r is guaranteed to be greater than or equal to 0 and less than mod b. So now what we need to do is replace mod a with negative a. So mod a is equal to minus a because a is negative. Therefore, this is going to become minus a is equal to qb plus r. We can now multiply everything through by minus 1. Minus 1 times minus a gives us a back again. So that's going to give us a is equal to, and then minus q times b, we can let the minus swallow into the q, so we'll get minus q times b. And then, so that's brilliant. That negative q is just an integer, so that's perfect as our quotient. The problem is then that we're going to end up with minus r rather than plus r. So actually, this is why I copied this bit that we have here into part 2. Remember, this is where we showed that if the normal Euclidean division is true for a positive remainder, then it implies that this modified version for the negative remainder is also true. What we didn't actually discuss is that the reverse is true as well. There is a biconditional here. The two are absolutely equivalent. So if this one is true, this one also is true. So that's what we're going to apply to our case that we're just doing, because we've got a negative version of the remainder here. So we want to use it to conclude that there will be a positive version of the remainder. But let me just talk you through why that's true. So if we start then with the bottom side being true, how do we conclude that the top is true? Well, it's just the reverse argument of what we did here. So let's do this. So we have our a and b, and we're supposing now that it's possible to write it as q bar times b plus r bar, where r bar satisfies that negative inequality, so it's less than or equal to 0, but greater than minus the size of b. So, and we want to show that it's possible to write it like so, with a positive remainder. So all we do now is again add and subtract mod b to both sides. Sorry, not to both sides, to the same side. So we'll get a is equal to q bar times b plus, in fact actually it's the other way around now, because we want the plus mod b to be with the remainder. So minus mod b plus mod b times r bar, not times r bar, sorry, apologies for all these mistakes, plus mod b plus r bar. And on the picture, and I will actually just redraw a bit of this picture out. So if we have our number line here, this is the integer number line, and then we have 0 here. Suppose we have b here, negative b here, negative 2b here, 2b over here, and then we might have a somewhere here. So we know that in this case we're going to the one on the left, and in this case we're going to the one on the right to have a negative remainder. To go from this one to this one, we thought about adding mod of b onto the quotient, i.e. bringing it forward. To go from this one to this one, we need to think about subtracting mod of b off the quotient so that we're going from the multiple that's on the right to the multiple on the left, which is what we're doing here. And then we'll have the plus mod of b plus the remainder here. So in the case that b is a positive number, mod b will just equal b, so you're actually subtracting off a b here, so you're going leftward. In the case that b is a negative number, then this will be minus b, so you'll be adding b on, and that is also equivalent to going leftward because b is a negative number. So you're adding on a negative number which is going leftward, whereas adding on a positive number goes rightward. So in that case, therefore, this is always going to take you to that quotient that's to the left of the one that you previously had, the q bar b. So I'll write this out. If b is greater than 0, mod b is equal to b, therefore q bar times b minus mod b is going to equal q bar minus 1 times b. In the case that b is less than 0, mod b will equal minus b, so q bar times b minus mod b will equal q bar plus 1 times b. But either way, that is going to be swallowed up, and we're going to have our new quotient. We're going to go back to our original quotient q, and then here is our new remainder, r. And of course, it is now going to satisfy this inequality. Because originally it was satisfying this inequality, and of course we weren't talking about the case when r bar is equal to 0. That's the case when there's no remainder, it's an exact multiple, and in that case it's obviously true that this is true. But in the case where the r bar wasn't 0, then it was properly in between these two, and then you just add now mod b onto both sides. This will become 0, this will become mod b, and therefore we get that r is between 0 and mod b. So hopefully I've convinced you that it works both ways then. If this is true, this is also true. So that's what we're going to apply back over here. So we now have a is equal to some quotient, this is an integer, times b plus minus r, which is going to satisfy the inequality that r bar would have satisfied, because remember the original r satisfied this inequality. We're now multiplying by minus 1, which reverses the order of the inequality here. So minus r, we can conclude, is going to be less than or equal to 0 and greater than minus mod b. So we've just multiplied this entire inequality through by minus 1, and it requires us to switch all the orders of the inequalities, so it would become this. So we've actually got here an r bar. We've got plus r bar, which is negative r, because it's satisfying this. So now, because of our theorem, we know that if it's possible to do this, it is also therefore possible to write it as some quotient plus a positive remainder. So unfortunately, we've used up our notation. This is our q bar and this is our r bar. It is possible to then, from that, find a q and an r. They're not going to be the same as this q and this r. That's why I'm talking about the fact that we've used up our notation. But because this is true, the original form of the Euclidean division is going to be true. So we'll stop with that argument there. I hope that's satisfied you. And then the final case is just more of the same. So let's now take a is less than 0 and b is less than 0. So again, we just take the modulus of the two and apply Euclidean division to them. So we know we can write mod a is equal to q mod b plus r, where r is going to be less than the size of mod b and greater than or equal to 0. And now we just replace mod a and mod b with negative a and negative b. So we'll get minus q times b plus r. Now, of course, what we want to do is multiply through by minus 1, so we'll get that a is equal to, and that negative cancels there, so we'll get just q times b. And then again, we've got minus r, where again, minus r is going to satisfy this inequality, that it's going to be less than or equal to 0, but greater than minus mod of b, because I've just multiplied this inequality through by negative 1. So again, here we have that altered form of the Euclidean division. We're saying we can write a as some quotient times b plus a negative remainder. And from what I've just demonstrated to you, if that's true, it's true that we can write it as some quotient times b plus a positive remainder. So we know from this that it's therefore possible to do. So we've therefore done all the cases. Just to go through all the cases that we've done again, not in full, just to look at the different cases we did. We did the case where a is equal to 0. We have then looked at the case where a is greater than 0, and we split that into two possibilities. Either b is greater than 0 or b is less than 0. That's over here. So we've proven it for both of those. B is never equal to 0, so we don't need to consider that eventuality. And then we looked at the cases where a is less than 0. Again, b is not equal to 0, so the two possibilities are b is either greater than 0 or b is less than 0. So we have overall covered every possibility for a and b and shown that Euclidean division is going to be valid for all of them. So to conclude then, this is correct. For any integer a and b, where b is not equal to 0, you can write a, the dividend, as some quotient times b plus a remainder, where that remainder is going to be a non-negative number that is less than the size of your divisor b. Also remember this modified form, that it's also possible to write it as some other quotient times b plus a different remainder, where this remainder is going to be the negative remainder, where it's going to be less than or equal to 0, but greater than minus the size of the divisor b. So thank you for watching. We'll end there.